Okay, that is our first lecture on composite structures. And that's going to be an introduction today. We will talk about some introductory features related to composite structures. First, we need to define what a composite material is. What's a composite material? What's the difference between a composite material and a conventional metallic material? What are the advantages of using composites? And what are the limitations and drawbacks of composite materials? Composite material types have to be introduced. There is a classification related to types of composite structures. So what are the types of composites? And what are their main features? And finally, today, if time remains, we will consider applications of composite materials and structures. It's going to be aerospace industries, automotive industries, marine applications, wind turbines, and we will give examples on such different applications of composites if time remains. Let me share the file first. This is chapter 1, this course. Its introduction. The course title is Introduction to Composite Structures. But first chapter is a review, actually. First, we need to define a composite material. What do we mean by composite material? In a composite material, two or more materials are combined on a macroscopic scale to form a useful third material. Characteristics and mechanical properties of this third material could be completely different from its constituent materials. You have material A and material B. You combine these by a certain manufacturing technique to produce a composite material. Now, let's say that's material C. But material C has completely different features, could have completely different features compared to materials A and B. And we expect that we will have certain improved mechanical properties in a composite structure. In this case, the materials are combined on a macroscopic scale. And that is the difference between a composite material and a conventional material. Because most of the time, if you do macroscopic examination of a composite material, you could be able to identify the components by naked eye. There are certain constituents. Some of them can be seen by naked eye, some of them cannot be seen, but at least some of the constituents should be visualized in a fiber reinforced structure, composite structure. There are fibers and matrix material, and if you take a cross-section of the structure, you should be able to identify the fibers and the matrix material. There are filler materials and other micro-scale additions. Of course, those cannot be identified by naked eye, but main materials And those are the fibers and matrix. They should be visible. And you can compare this to a regular metallic alloy. Metallic alloy is a mixture of materials. There are different types of metals and other additions. But the resulting structure is macroscopically homogeneous. And it's not possible to distinguish these different components by naked eye. It's assumed to be a macroscopically homogeneous material, a regular metallic alloy. But composite material is not homogeneous. We should consider, or we will consider, the assumption of homogeneity in certain mathematical models. But in actuality, the material is not homogeneous. There are fibers or particles or other additions, or there are different layers in a composite. So it's not as homogeneous as a metallic alloy. Those are the main features of composite materials. Another definition is given in this slide. These are macroscopic combinations of two or more distinct materials having a discrete and recognizable interface separating them. There are interfaces, or there is an interface in a composite structure, unlike regular conventional metallic alloys. And what do we mean by an interface? You could have a cross-section like this. It's a cross-section. And I can embed a particle or a sphere in this material. That's reinforcement. And the boundary of this particle and the surrounding matrix is an interface. It could be a particle as well as a cross-section of a fiber. It's a fiber reinforced composite. That could be a cross-section of a fiber. And then the circular border is the interface. So hence, in a composite structure, we have recognizable interfaces. There are no such interfaces in a regular homogeneous metallic alloy. It is an important distinction between a composite material and a conventional metallic material. And why do we use composites, or why do we need composites, or why are they developed in the first place? There are certain advantages, and they exhibit best qualities of their components. You may have two different components or materials, but when you combine them, you will fabricate a completely different structure, which will possess certain advantageous properties and features. What are these in a composite material? A main feature or an important consideration here is the weight. In fiber reinforced composites or certain polymeric materials, there is the possibility of weight reduction, in which in certain industries, weight is a critical concept. One of them is the aerospace industry. As an engineer, your task is to minimize the weight of a structure while maintaining the strength. It could not be possible by regular metallic materials, by steel or aluminum, titanium. You may not reduce the total weight of the structure to a level required by design specifications. But when you use composite, you open the possibility of significant weight reduction. So weight reduction is an important advantage of quality of composite structures. But while reducing the weight, we keep the strength intact. The material has high strength, as you will see later. A composite material or a structure could have high stiffness in an elastic body. Which mechanical property is representative of the overall stiffness? That's a question for you. Suppose that we have an elastic body, and then which, yes, Shane gave the correct answer. Young's modulus is representative of, let me open this. Young's modulus is representative of stiffness in a composite body. In certain composites, Young's modulus is larger than those of the metallic materials or conventional materials. And which material property could be representative of the strength of the material in a regular structure? Which material property represents strength? Yes, there's an answer. As Shane and Mohammed gave the correct answers. So ultimate tensile strength is generally representative of strength. It could be yield strength, but in composites analogy, we will be talking about ultimate tensile strength. We will deal with ultimate tensile strength of composite structures. And composite structures generally have much larger ultimate tensile strength in certain directions compared to regular conventional materials. Even relatively less expensive composite material has 4 times, 5 times strength of that of conventional steel. It's possible to have such large strength values for composite structures. And high strength, high stiffness, and low small density or weight are important considerations in design of structures in different engineering applications. These are aerospace, automotive, marine applications, wind turbine, and all other possible applications in engineering may consider use of composite structures. And depending on the particular type of application, it could be possible to develop a certain or different type of composite material which have improved certain other improved properties. This could be wear resistance. This is encountered in applications where there is contact between different material bodies. Sliding contact causes wear. And to reduce wear, you might employ composite bodies or structures. Fatigue life is an important consideration in engineering. And this can be improved by applying composite structures. Fatigue life. Temperature-dependent behavior is important. You can minimize the sensitivity of the material to temperature variations by using composites. We will see. We will We are going to have a detailed discussion on temperature variations and thermal effects. Acoustical insulation is a particular requirement. It could be possible to overlay a composite coating or a certain structure to improve acoustical properties or acoustical insulation properties. Those are certain advantages of or features of composite materials. And there is a table here. You could find such tables in different books on composites. I have taken this from one of the books. I don't remember which book that was, but it's a detailed list of advantages and disadvantages of composites. And we have talked about advantages, but there are limitations as well. You should be aware, as an engineer, you should be aware of the limitations and disadvantages. And what could be the disadvantages of or limitations? One of them could be the cost, which means that you might need to do a cost analysis. What is the cost of a structure made out of composite systems? What's the cost of a structure made out of regular systems? And does the application or service condition justify the use of high cost material? Lack of well-proven design rules. This could be a disadvantage maybe 10 years or 20 years before. But right now there was an immense volume of research on composites design rules, and their behavior are thoroughly understood today. I don't think that is a disadvantage at the current point in time. Now, depending on the application, it might not be possible to change the metal by a composite. There could be certain requirements which might not allow you to replace the existing design. Long development time, if you are investing in manufacturing technology, it will need some time and investment, of course, and it might require some long development time. You need to have experience on manufacturing method. These two could be important limitations, actually, here. Moisture attack and temperature limits. These, depending on the environment conditions, you might need to further improve your design to counter the problems associated with moisture diffusion and temperature variations. Most commonly used materials, the composite materials are polymeric. Plastics or polymers are main constituents. And of course, they do not have high resistance to high temperatures or high heat flux values. If very high temperatures are encountered in an application, of course, you could need to use metallic material or ceramic coatings are used for thermal protection. But if it is not the case, if there are not such extreme variations in temperature, or if you can do a design to overcome these difficulties, composites could be a good alternative to the existing conventional materials. Any questions about advantages or disadvantages of composites? There are other details here hidden damage, cracking or damage susceptibility. That could be low ductility whenever there are stress risers. Depending on the application, it could be necessary to consider such different possibilities, of course. And the advantages are listed in this column. We have already talked about the lightweight composites, high specific stiffness, and high specific strengths. What is specific stiffness? I mean, you have stiffness and a specific stiffness. What do we mean by specific stiffness? Does anyone know?
Strength to weight ratio, is it?
Yes, that is the correct answer. That's an important point. Yes, strength divided by weight or density or specific weight. Any of these can be used, strength to weight ratio. That's right, and it's an important consideration. In a composite body, you have high strength. The strength is larger than that of metallic materials in certain directions. There's high strength, and its density, the effective density is smaller than that of metallic material. So this ratio, strength over density or specific weight, is much larger than that of the metallic material. And for this reason, these materials are known to have high specific stiffness and high specific strength. Another important consideration is tailored properties. We can talk about this. We can allocate a large amount of time on this because this is a critical issue in composite structures, especially in fiber reinforced composite materials. These materials are not isotropic. They are anisotropic materials. And there is a high degree of anisotropy in composite structures. And what do we mean by anisotropy or anisotropic materials? What do we mean by this? Does anyone know? Is there an answer? Yes, you can answer.
Material do not experience the same strength in different layers, in different orientations, I mean.
Yes, that is an important point. That is the correct answer. It's an important point in composite structures. There is a variation of material properties with direction. You might have X and Y axis, for example. X axis is along the plates in the longitudinal direction, and Y axis is perpendicular to the X axis, of course. In X direction, you have a certain margins of elasticity or strength. So you have a certain stiffness in X direction, and a different stiffness is in Y direction. And if fibers are oriented in X direction, the material is much stiffer in X direction. And you can rotate this axis. There are different orientations, of course. For example, that could be a 30-degree axis, and an axis inclined at an angle of 30 degrees with the x-axis, and you'll get a different stiffness for that axis as well. So the properties are changing with direction, with the orientation of the axis. This is not the case for metallic materials, for regular materials. Materials, for example, you study in design courses and machine elements courses, you always assume that there is isotropy. And material properties are same in all coordinate systems, but there is a variation. But the good thing about this variation in composite structures is that you can control the variation. And you can, by designing the composite in a certain way, you can change the variation, and it will be possible to manufacture composites that have large strength and stiffness in desired directions. So the engineer can come up with a design which will lead to high strength and stiffness in desired directions. That's an important advantage of using composites, because you cannot do this in regular conventional metallic materials. In a metallic material, in X section, elastic modulus is 200 gigapascals, the steel. But in Y direction, it's the same. And in any direction in between, the stiffness and strength, they are all the same. But you can control the variations in stiffness properties of and strength properties of composite materials. It's possible to do that. And there are many parameters that you can control when you design a composite. This can be done by changing the directions of fibers. You can change the number of layers or materials of the fibers, total thickness. So there are many different design parameters. Therefore, you may develop a code, as we will see, and each property can be changed to tailor the overall mechanical response of the composite body. I will talk about this, and at the end of this course, you'll be able to develop such programs, and you'll be able to carry out such computations. And other advantages are listed here. These are easily moldable. In one way or another, these molding processes are applied in composites manufacturing. We will talk about this. Part consolidation is possible. Fewer amount of parts might be necessary. Bondable to other types of materials using different types of joining methods. So, and each of these can be examined, and particular materials leading to improved properties can be used. Fatigue resistance is important. Damping, internal friction can be changed. Crashworthiness, such polymer-based materials could be used in applications where there's a concern on crashworthiness, and some other properties are also listed here. Thermal expansion coefficient, electrical conductivity, stealth, and thermal transport properties can be changed by changing the constituent materials used in a composite structure. So these are listed in different sources, and you should be aware of main advantages, limitations, drawbacks of using composite structures. And this figure illustrates some of the variations in properties of materials. This one, for example, shows the weight of these three different materials: weight of steel, aluminum, and composites. They are shown, and composite weight is much lower than that of steel. Aluminum has a comparable weight here. can compete with composites when you consider weight. But this is just a general picture, and in composites, there is a variation in weight, of course. If you use, that depends on the type of material, constituent material you use. Different types of materials, fiber materials and matrix materials are available. And depending on the type of material used, you will end up with a different density, overall density and weight. Thermal expansion coefficient can be minimized in a composite structure. You can design it to fabricate a composite structure with 0 thermal expansion coefficient in a certain direction. It's possible to do that. So there won't be sensitivity to temperature in a certain direction. It's possible with composites, and metallic materials generally have higher thermal expansion coefficient values as shown here: steel, aluminum. They have larger thermal expansion coefficients. And specific strength is indicated here. As we have just mentioned, the specific stiffness is stiffness modulus of elasticity in a certain direction divided by density or specific weight. And composites, materials, or structures have the obvious advantage here when you consider specific stiffness. Steel and aluminum generally have much lower specific stiffness values compared to composites. And the same situation is observed here for specific strength. And fatigue resistance can be improved by using composite structures instead of regular metallic materials. And these visuals are representative of advantageous features of composite structures. We have considered some advantages and limitations of composite structures. We have listed them and we have discussed them. And we have a main definition for composite bodies: a combination of two or more different materials on the macroscopic scale, and there should be visually observable interfaces between these different phases of composites. We can talk about the applications. What are the applications? How are these materials developed? What were the first use cases of composites? We can talk about this. We have some time, and we can talk about such applications of composite structures. The history is actually longer than we might think about. One of the first composite materials used were bricks, actually, and they are still used in 21st century in different parts of the world, and even in this country. These bricks are made of clay, and they are reinforced with straw. As an illustration of a composite material, Israelites first used such structural materials. The role of a straw is reinforcement in such a material. And clay is the matrix material. And straw actually reinforces the material in different directions, and it might actually inhibit crack propagation within the material. And for this reason, such components have been used for thousands of years in different parts of the world. And fiber reinforced composite is a modern version, actually, of this material. Another material is mentioned here, and it's also mentioned in different sources on uses of composites as plywood. You have a number of layers in a plywood, as shown here. How many layers do we have here? 1, 2, 3, 4, 5, 6, 7, 8. 8 different lamina or layers. Now, wood is a fibrous material. And in the first material, for example, the fibers are aligned in this direction. And in the second material, there is a rotation and the fibers are aligned in the other direction. And by using these two directions perpendicular to each other, we have a somewhat reinforced structure, a structure reinforced in two different directions. So its performance is expected to be better than regular materials consisting of wood. It's called plywood, and it's used as a structural material as well. Now, this is a concept. This is the concept of lamination. A modern concept is fiber reinforced laminated structure. And in modern applications, you may have reinforcement in any direction you want. This kind of variation is referred to as cross-ply composites. Cross-ply. In a cross-ply, the fibers are perpendicular to each other, as shown here. And this is the case for plywood. It has been used for thousands of years as an engineering material. These were some examples, but what is the modern classification for composites? What is the existing classification? Actually, there is there could be different composite materials as well. Some of them most commonly encountered ones are listed here. There's the main classification. But there's a high volume of research going on. And scientists or engineers are developing new materials every day, proposing new structures and materials. But this is a main list, and it includes most commonly used modern composite material. The first one is fibrous composites. It consists of fibers located in a matrix. Bricks made of clay and straw was an historical example to fibrous composites, but that's one of the main composite materials currently in use today. The second one is laminated composite materials. Plywood was an historical example. It consists of a number of layers with different properties. It's called lamination. You can think about laminated glass. We will talk about it. Or other laminated materials. There are particulate composite materials which comprise particles in a surrounding matrix. There are many examples of this in material science and engineering. Another main item is flake composite materials. They are composed of flakes embedded in the matrix. Again, functionally graded materials, another type of composite. In this case, again, that is a multi-phase composite. There are there could be a number of materials in a functionally graded material, and it could be used as a protective coating. This one could be coating, and coatings are used to protect substrate materials. That's a substrate, for example. The substrate is, in certain applications, substrate is metallic. Ceramic coatings, for example, are used for thermal protection. In a functionally graded material, this coating is 100% ceramic at the surface, which is exposed to high temperatures. Volume fractions are changed through the cross-section, and at the other ends, the material is 100% metallic. And this provides or leads to improved bonding between the coating and the substrate. And there is a smooth variation in between. Here you have 100% ceramic material, and here 100% metallic material, and there is a smooth variation, and these variations are described by mathematical functions. It's possible to describe these variations by continuous functions, power function, exponential function. And such materials are called inhomogeneous materials. And that is another important definition in the study of composites: inhomogeneity and anisotropy. These are different concepts. Inhomogeneity is described here. The material property, for example, elastic modulus, depends on the location of the point. It's called spatial variation. At this point, you have a different elastic modulus. At the interface, there is a different elastic modulus. There is a variation. This is called inhomogeneity. We have talked about anisotropy as well. It's something different. And anisotropy stems from rotation of coordinate axis. Anisotropy is related to direction. Inhomogeneity is related to position. So there's a difference between direction and position. But those are important concepts needed to understand main features of composite bodies, composite materials. Fibrous composites. Actually, all composites are inhomogeneous. Fibrous composite, inhomogeneous. All of them are inhomogeneous because different materials are used in their fabrication. But not all of them are anisotropic. A functionally graded material could be isotropic. That could be a variation with position, or particulate composites could be perfectly anisotropic as well. But fibrous composites, they are not isotropic. They are anisotropic materials. Now we will talk about these in this first chapter. We will talk about main features of these different types of composites. Actually, we have listed number of materials, composite materials, fibrous composites, laminated materials, particulate composites, flake composites, functional grade materials. And if you do research, you will be able to find different types of composites as well. And there are no limitations. As an engineer, you may end up with different configuration. But we will talk about properties of these different types of materials. What are the main features of fibrous materials? What are the properties of laminated materials? Or what are the main uses? What are the examples? We will talk about this in the upcoming lectures. Therefore, this is the end of the lecture for today. I'm going to stop the recording right now and we will continue next time on Monday.